Hi, my name is Amy, and this is my research titled Electrostatic Tractor Effectiveness in a Non-Maxwellian Geoplasma Environment. Let's get started with some background. This research is a continuation of the work related to the electrostatic tractor, which is a concept for contactless debris removal in GEO. The concept states that a servicer spacecraft aims an electron beam at a target debris object. The impact of the electron current on the target causes it to charge negatively, while the electron emissions charge the servicer positively. An attractive force that allows the servicer to reorbit the debris to a graveyard orbit is the result. We focus on GEO for a few reasons. First, the spatial density of objects in GEO is relatively high, and 95% of all insured satellites reside there. Despite that, around 50% of satellites are non-compliant with IADC regulations at the end of their life, falling short of the suggested graveyard orbit or being completely abandoned. In addition, contactless debris removal is essential for geodebris because defunct spacecraft have been observed to tumble at rates on the order of tens of degrees per second. Finally, the typically low density of the plasma environments prevents debye shielding that would prevent the electrostatic force to be felt over suitable distances. The low density of the GEO environment also means that non-thermal particle distributions are present. This work examines three possible distributions in the GEO environment. First, the bi-Maxwellian plasma, which is a combination of two Maxwellians. The bi-Maxwellian plasma would be the result of substorms which occur every few hours or geomagnetic activity that causes a slight compression of the magnetosphere. Next is the kappa plasma, which is simply a Maxwellian plasma with a parameter kappa that determines the slope of the superthermal tails that make up the tail of the distribution function. The superthermal particles that make up the tail of the distribution function. This would likely be the case between substorms and also during severe geomagnetic storms, during which geosatellites are exposed directly to the solar wind. The third case is the cool Maxwellian core and hot kappa halo, a more complex representation of substorms or storms. Okay, let's get started and talk about the bi-Maxwellian plasma. The flux for a bi-Maxwellian plasma is simply the sum of the flux for two Maxwellian plasmas. The result is seen here in the figure. The charging threshold refers to the onset of negative charging in a particular space environment. In a bi-Maxwellian plasma, variations in the environment can cause the potential to jump between negative and positive potentials. This figure shows the charging threshold curve at a particular T2. Increasing T2 would cause the curve to shift upward. The key is that the initial target potential does not dictate the value of the equilibrium potential, as that's decided on entirely by the environment. The electrostatic tractor was simulated in two different bi-Maxwellian environments, a more mild environment and a worst-case environment from Schaub emission data. The couple charging effects are included in these simulations. In the figures, the lines are colored based on the electron density ratio alpha being either less than or greater than 1. You can see that when alpha is less than 1, perturbations in alpha can cause more severe equilibrium jumps. And as alpha becomes increasingly large, the equilibrium potential converges in both figures. In the worst case environment, the potential jumps to a positive value when alpha is small, which could cause problems for the E-tractor. So let's take a closer look at the worst case environment. Notice that there's only a right side equilibrium in this environment, meaning the case where the electron beam cannot initially impact the spacecraft does not exist. The forces and torques are calculated using the multisphere method. If we look at the forces on the target over the full range of alpha, we observe that the force is only greater than 0 in one case, despite the target reaching a positive potential in 4 cases. Greater than 0 implies a repulsive force, and less than 0 is an attractive force. It turns out that the electric field from the servicer is substantial enough to cause induced charging effects on the target, meaning that despite having a positive potential, the charges on the target are still negative overall. All right, let's move on and talk about the kappa plasma. As I mentioned earlier, the flux of a kappa plasma is simply a Maxwellian that includes the spectral index kappa, which determines the slope of the superthermal tail. Note that as kappa goes to infinity, the flux converges to a single Maxwellian. Here, I'm just showing that the temperature required for the onset of charging in a kappa plasma linearly increases with kappa. The active charging simulation in the kappa plasma with various values of kappa ranging from 1 to 10 is shown side by side with the active charging simulation in a single Maxwellian plasma. You can see again how as kappa becomes larger, the charging response matches with that of the single Maxwellian. There are three key observations here. As kappa gets smaller, a jump occurs from the right to the left side equilibrium. Also, when kappa is small, there are equilibrium jumps that occur with perturbations in the environments. And last, the right side equilibrium is positive for some smaller kappas. Since there's a left and a right side equilibrium, we'll take a quick look at the force and torque results from both. The so-called right side equilibrium here are essentially the points where the initial potential of the target was less negative, such that the electron beam could initially impact it. The force results are fairly interesting. The first thing you're likely noticing is the huge jump in the middle of the points. That jump is where kappa became negative enough to cause a jump from the right side equilibrium to the left side. The next thing you'll notice is that on the larger side of kappa, there's a sharp corner as the points converge. The corner is a place where the spacecraft potential changes from being positive to being negative as kappa increases. When the spacecraft potential is positive, the electrostatic effect is different than when the spacecraft potential is negative due to the electric field of the servicer. This is the same reason why the force is always attractive, despite both the target and servicer having positive potentials. Let's look at the left side equilibrium now. This is less exciting than the right side equilibrium, but we can see how variations in kappa and the subsequent potential jumps impact the force and torque acting on the target. Finally, let's take a look at the Maxwellian core kappa halo environments. The flux for the Maxwellian core and kappa halo environments is simply the sum of a Maxwellian for population 1 and a kappa for population 2. You can see in the figure how the population 2 flux converges to Maxwellian as kappa goes to infinity. At that point, the flux is the same as a bi-Maxwellian plasma. Here you can clearly see how the charging response becomes bi-Maxwellian as kappa goes to infinity. You can also see the same potential jumps we saw in the kappa plasma when kappa is small. Again, we'll look at the forces and torques for both the right and left side equilibrium. For the right side equilibrium, notice how the force in the y direction increases as kappa increases and then decreases as the force converges. This is likely related to the electric field of the servicer, but I'm not really sure. Again, the left side equilibria are not as exciting. But you can see how the force converges as kappa increases. This is a summary of the topics I discussed in these slides, but I would really recommend checking out my paper for more details if you're interested in the non-Maxwellian plasmas. There's a lot of supplementary information for what I talked about today. Thanks for watching.